Lesson 9.1, Properties of Radicals. You should be on page 480. In this lesson, you will learn properties of radicals and how to use them to simplify expressions, how to simplify expressions by rationalizing the denominator, and how to perform operations with radicals. Now, a radical expression is an expression that contains a radical. And there's two key properties we have to understand before we continue. The first one is the product property of square roots. Here's what this is trying to show you or tell you. I am allowed to multiply radicals together is what this is basically saying. So for example, let's say I had the square root of 3 times the square root of 5. I am allowed to combine those together into the square root of 15. I can multiply radicals together. Now, I want to quickly show you one thing I cannot do. Okay, I'm going to do this in red because I can't do this. I could not take 3 and multiply it with square root of 5 and call that 15, square root of 15. I can't do that because these are not both radicals. So I can multiply radicals together, but I'm not allowed to multiply a whole amount and a radical and somehow combine those into something under a radical. So that's what the product property of square roots is trying to show you. Next, we have a quotient property of square roots. And remember, quotient means divide. So what this is trying to tell you is you can divide radicals. Okay? For example, I could take the square root of 30 divided by the square root of 5, and that would be the same thing as taking the square root of 30 divided by 5, which would be the square root of 6. I can do that. Okay? This property I can also use in reverse. If I had, let's say, the square root of, I'm going to put 40 over 8, I could break this up into the square root of 40 divided by the square root of 8. It would give me the square root of 5. I can divide radicals. Okay? Here's one thing I can't do. Okay, so let's make this clear. If I'm just going to make up something simple again. Let's say I had the square root of 24 and it was divided by 6. I cannot make that equal to like 4. I can't take 24 divided by 6 and just call it 4 because I have a radical here, I don't have a radical here, so I cannot divide those and make it into 4 somehow. I can divide radicals. Now that we've seen that we can multiply radicals and divide radicals, we can talk about simplifying radicals. And as an expression involving a radical is in simplest form when these 3 conditions are met. Okay, so there are 3 rules to writing a radical in simplest form. Here's rule number 1. You cannot have any radicals with perfect squares other than 1. Now, I wrote that here off to the side, okay? Because that's a little bit more technical. This is what the blue highlighted wording is trying to tell you. You cannot have perfect squares trapped inside a radical other than 1. Okay? Now, let's go through, this is a little list. I had you write this down earlier in the year. These are perfect squares. Like 4 is a perfect square. The square root of 4 is 2. 9 is a perfect square. The square root of 9 is 3, and 16 is a perfect square. The square root of 16 is 4, and so on. You have to remember these in order to follow this first rule. We never leave perfect squares inside of a radical. That's the first rule. The second rule. We never leave radicals or fractions inside of radicals. And maybe you just want to write it down this way in your notes. Never leave a fraction in a radical. So here's rule number 1. Never leave a perfect square trapped in a radical. Here's rule number 2. Never leave a fraction in a radical. And now rule number 3, which is never leave a radical in the denominator. So you have simplified a radical if you followed these three rules. Never leave a perfect square inside a radical, never leave a fraction in a radical, and make sure you never leave a radical in the denominator. You might want to write those three rules just the way I wrote them here, okay? That's probably the simplest way I can state those. So let's look at some sample problems here where we're simplifying a radical. So here's a problem. It's the square root of 108. Now, 36 goes into 108 three times. So I can break 108 in the square root of 108 into the square root of 36 times square root of 3, which is the square root of 36 times 3. And what is the square root of 36? It's 6. So I can rewrite this as 6 square root 3, and I just simplified the problem. I just addressed rule 1 that we just talked about on the previous screen. 36 is a perfect square, and it was trapped in the radical. The square root of 36 is 6. I just simplified that radical. Or if you look at the second example, I can break this up into square root 9, square root x squared, square root x. So let's make sure you understand where I'm getting this part from. Do you see how I have x to the third power? I can break that up into the square root of x squared and the square root of x. If you multiply those together, you get back to third power. Here's why I broke it up, though. The square root of 9 is 3. The square root of x squared, what times itself is x squared? It's x. So I got both of these perfect squares out of the radical. That's rule number 1. You never leave a perfect square in a radical. And the square root of x, there's no perfect square trapped in there. So I just simplified that. So these three rules that we're talking about to simplify a radical, we never leave a perfect square trapped inside of a radical. And that's what these two questions were about. There were perfect squares trapped in the radical. In the first question, 36 was trapped in a radical. So square root of 36 is 6. And in the second question, 9 and square root of x squared and 9 are perfect squares. They were trapped in the radical, and we got them out of the radical. What I would like you to do is try these 4 questions. Pause the video and try simplifying these radicals. And I'm back, and I simplified the radicals, and I circled my answers. So if you're not sure with these, make sure you ask in class. It's very important that you know your perfect squares, which was that list I showed you. If you don't remember the perfect squares, 4, 9, 16, 25, 36, 49, etc., you're going to really struggle on this. We have to know our perfect squares. We might have to simplify radicals that are involved with fractions. Now remember, the second rule is we never leave a fraction in a radical. Okay? So if you look at question A, do you see how we have a fraction in a radical? Well, that's an easy fix. Okay? We can get the fraction out of the radical. All we have to do is break this radical up into separate radicals. The square root of 15 over 64 would be the same thing as the square root of 15 over the square root of 64. Now, isn't that a perfect square? The square root of 64 is 8. The square root of 15, there is not any perfect square that goes into 15. I just simplified this. So the square root of 15 over 8 would be simplified. Okay? I do not have a fraction trapped in a radical anymore. And then look at B. I have a fraction trapped in a radical. So what they did first is, you notice, they broke this up into separate radicals. I have the square root of 81 on top, and I have the square root of x squared on the bottom. Now, 81 is a perfect square. The square root of 81 is 9, and the square root of x squared, that's a perfect square. X, 9 over x. I just simplified this. What I have just talked about can be extended to other radicals like cube roots. So they will have a few cube root questions. Now remember, cube root means what times itself gives us that. Cube is third root. Okay? So when you look at some of these examples, okay, we are trying to find what times itself would give us this. So if you look, for example, at example A, they give me the cube root of negative 128. So let's think. I can break that up into the cube root of negative 64 and the cube root of 2. And you're like, why would I do that? Well, think about it. Isn't 4 times 4 times 4 64? So the cube root of negative 64 would be negative 4 times negative 4 times negative 4. So this works out to negative 4, and I have the cube root of 2. 2 is not a perfect cube, but I got that negative 4 out of there. That was trapped. So again, when you have cube roots, we're trying to find a perfect cube that I can get out of the radical. Any perfect cubes I can get out of the radical I want to do. Okay? We'll do one more just so you can see it. Let's look at this question. Okay, so I have the cube root of 125x to the 7th. Okay, now 125 is a perfect cube because 5 times 5 times 5 is 125. Now x to the 7th is not a perfect cube, but x to the 6th is. Now think about that. Wouldn't x squared times x squared times x squared give me x to the 6th? Okay, so I'm going to rewrite x to the 7th in this way. Can you see I'm going to circle this or box it? If I combine those two together, I have x to the 7th. So I'm just breaking x to the 7th up into x to the 6th and x. Now, let me highlight. That's a perfect cube. 5 times 5 times 5 is 125. This is a perfect cube. Let me highlight it again. X squared times x squared times x squared is x to the 6th. And this I can't, that's trapped. The x is trapped in the radical. There's no perfect cube there. I just simplified that, okay? So we will be asked in the homework sometimes even, not a lot, but you should be able to solve or simplify some basic cube root problems as well, okay? I would like you to try the even problems from 6 to 12 here. Pause the video and try those. And I'm back, and I wrote my answers and circled them. So again, if you're struggling on this and you're stuck, make sure when you come to class tomorrow, ask about it, and we can walk through step by step, if need be, how I'm getting these answers for these that I circled. Now remember, rule number 3 of simplifying radicals was you never leave a radical in the denominator. So the process of not leaving a radical in the denominator is called rationalizing the denominator. So we never leave a radical in the denominator. So let's take a look at some sample questions here, like square root of 5 over square root 3n. I'm going to write it off over here. Okay? Now, I can't divide 5 and 3. There's nothing I can do here. So what we're going to do is called rationalizing the denominator. It's very easy to rationalize the denominator. You take whatever radicals in the denominator, and in this case it's radical 3n, just quickly go ahead and multiply the numerator and denominator by the same thing. Now I want you to think for a minute before I continue. Isn't radical 3n divided by itself 1? I'm multiplying this by 1. Multiplying something by 1 doesn't change its value. So what I'm doing is I'm changing what this looks like, but it's not changing the value. I'm multiplying by 1. So let's do that. Radical 5 times radical 3n would be radical 15n. Down here, I have radical 3n times radical 3n. So I have square root of 15n on top. But now think about down here. I have 3 times 3 down here, which is 9. And I have n times n, which is n squared. And you notice 9's a perfect square. so is n squared. So square root of 9 is 3, and the square root of n squared is n. I just rationalized the denominator and simplified the expression. That could happen in cube root questions as well, like what they're showing you here. I have 2 over the cube root of 9. Now, 9's not a perfect cube, but 27 is, right? Isn't 3 times 3 times 3 27? So if I multiply the numerator and denominator by the cube root of 3, look what I get. I get 2 cube root 3 on top, but on the bottom I get the cube root of 27, and the cube root of 27 is 3. So 2 cube root 3 over 3, and I just simplified that. If you have a binomial with a radical in the denominator, you will need to use what's called a conjugate. So you're like, what the heck's a conjugate? Okay, it's a pretty simple thing. A conjugate is the same binomial, but one is addition and one subtraction. So look at this question, because this question has exactly what I'm talking about. Do you notice how we have a binomial in the denominator, and we have a radical in it? Okay? Here's what a conjugate is. I'm gonna highlight it here in green. To get rid of 2 minus radical 3, I would multiply the numerator and denominator by 2 plus radical 3. You see how I have 1 minus, one's binomial subtraction, one's addition. Now you might be like, why do I do that? Okay, well let's focus down here why I'm doing that. I need to double distribute, or do you notice the sum and difference pattern? 2 times 2 would get me 4. So in the denominator I have 4. And radical 3 times radical 3 is radical 9. And I'm going to subtract these. Well, that would be 4 minus radical 9 is 3, which gets me 1 in the denominator. So that's why my denominator is 1. Do you notice my radicals went away? Now in the numerator, I have to take 7 and multiply it with 2 plus radical 3. Well, that's easy to do. Distribute, I get 14 plus. Now remember here, 7 and radical 3 does not turn into 21. These are not both radicals. I would just write 7 radical 3, and that's what I end up with. I end up with 14 plus 7 radical 3 over 1, which is 14 plus 7 radical 3. What I would like you to do is try the evens here from 14 to 20. Pause the video and do that. Okay, and it's the same thing. I'm back. I circled my answers to 14, 16 is down here, 18, and 20. A couple of these problems require you to use conjugates. Each of these questions will have you having to rationalize the denominator. We can't leave radicals in the denominator, so we had to rationalize the denominator. Again, if you're stuck on that, make sure you ask about it in class. We can go through these in more detail if what I have here isn't making sense to you. This next page, I'm going to skip through this because these questions are word problems. On the word problems, you can just type these in your calculator because we're not simplifying radicals. We're actually able to put these in and just type them in and write the decimal answer. You can see these are answered in decimals. So it is legal for you to just put these in your calculator and have your calculator produce the correct response. Okay? To wrap up the video, performing operations with radicals. Okay? Radicals with the same index and radicand are called like radicals. You can add and subtract like radicals. Okay, so for example, 2 radical 3 plus 5 radical 3 would equal 7 radical 3. It's a lot like variables. Think about it. If you had 2x plus 5x, you'd get 7x. If you look at my example that I just wrote above that, I have like radicals. The square root of 3 is a like radical, so 2 square root of 3 plus 5 square root of 3 would be 7 square root of 3. Okay? And by the way, that works with subtraction too. Like if I had 6 radical 2 minus 8 radical 2, I would get negative 2 radical 2. I have like radicals. Okay? Now here's one thing I cannot do. Better be clear on this. Let's say I had 3 radical 2 plus 5 radical 7. Okay, do you notice? I'm going to highlight these radicals are not alike. This is radical 2, this is radical 7. I can't, and I have people do this each year, I cannot call this 8 radical 9, for example. This would not be correct. I can't take 3 and 5 and make it 8 and 2 and 7, add them up and call it 9. These radicals are not alike. It'd be like, here would be a sample of what I'm trying to show you. It'd be like having 3x plus 5y. My variables aren't alike. I can't make that into 8. These radicals are not alike. I cannot add or subtract them. So when you look at these examples like up here, do you notice in this question here, I have like radicals. The square root of 7's alike. So 5 radical 7 minus 8 radical 7 would be negative 3 radical 7. And the plus radical 11 I can't do anything with. It's not alike, so there's my answer. Negative 3 radical 7 plus radical 11. Okay? Look at B. 10 radical 5 plus 20. Now these are not alike, but I want you to notice something. Radical 20 can be simplified. Think about it. Doesn't the perfect square 4 go into 20? So I have 10 radical 5 plus the square root of 20 would be the same as radical 4 times radical 5. Isn't the square root of 4 2? And if the square root of 4 is 2, I now have 10 radical 5 plus 2 radical 5. Those are alike. Those would add up to 12 radical 5. Okay? And here, look at this. I have like radicals. I have 6 times the cube root of x plus 2 times the cube root of x. These radicals are alike. That would turn into 8 times the cube root of x. You can also multiply radicals, okay? And we've already learned about multiplying radicals earlier. So in other words, that allows me to distribute. Like here, I can distribute. Radical 5 times radical 3 is radical 15. Radical 5 times radical 75 would be radical 375. Now, 15 does not have any perfect squares. 375 does. Think about it. 25 times 15 is 375. So I could break up that into radical 25, radical 15. This would be square root of 15 minus 5 radical 15. So this is 1 radical 15 minus 5 radical 15. That would be negative 4 radical 15 to produce that solution. I'm going to pause the video here. If you have questions, make sure you ask in class.